Excellent.
Oh dear. Yeah, because it looks like there's like a green light around their thing, but I can't hear them. Can you?
Yeah. They're
Oh, you
on this
can.
right now, I think.
No. Nicole, we can't hear you. Can you hear us?
Yeah.
Oh dear.
Okay.
Yeah.
Ah.
Okay, Jeremy. Hello.
Hello.
It's Matt here, the session chair. I've introduced you already when you couldn't hear, so you should just start.
Sorry. Oh, in that case, I will. Thanks so much. Good. Apologies for all the technical difficulties. Thanks for bearing with us, everybody. And yeah, good evening from Glasgow. Unlike lots of Scottish people who made it to World Cup in America, we're still in Scotland. But yeah, we're really glad to be able to tell you about our paper on interpreter memory safety via differential fuzzing with a cherry on top. So this is joint work between Kai and myself at Glasgow University and Huanting and Zheng at Leeds University. So just to give away everything in a single slide, we synthesized a big corpus of Python code, which tickles the internals of the runtime. About 8,000 programs, lots of them cause problems. And that was our intention, really, because we're looking for bugs in the runtime. And the particular runtime we're working with is MicroPython. We've got two separate builds of MicroPython. One is CHERI memory safe runtime, and the other is a non-CHERI conventional runtime. So we run the code on both and look to see what the differences are in the results. And at the end of the day, we find some real memory bugs in the MicroPython runtime. We found 51 bugs, 3 of which turned into GitHub issues and 2 of which have been patched. So I think there's a happy ending to our story. Yes, you might be thinking, why on earth do people have high-level language runtimes on microcontrollers? And here's an ESP microcontroller here. And I remember whenever I used to go to electronics classes and people would put up pictures of circuit boards, they always put a coin next to them. And I think it was to show the kind of relative scale of their circuit boards and so on. But actually, these kind of microcontrollers these days can be bought for pennies. They're really, really cheap. And they're very constrained hardware, you know, with kind of kilobytes of RAM and perhaps kilohertz processors. But even on such constrained embedded devices, people want to run high-level languages like Python and JavaScript and WebAssembly. This might be for accessibility, you know. Kids these days can only program in Python. Might be for prototyping, maybe to do some kind of rapid development of simple IoT applications. Maybe for memory safety, Python, purportedly, JavaScript and WebAssembly are memory safe in some sense. And maybe for portability, you can kind of move these higher level programs across different microcontroller families and architectures. But the point is, the underlying runtime is going to have to be a legacy C application that does have manual memory management. And that's exactly how MicroPython, the runtime we're looking at, is implemented. It's C code underneath. Okay, so here's what the von Neumann architecture looks like on a microcontroller. The processor talks to the memory, and there's no interposing memory management unit. You know, we've only got physical addresses to work with. There's no memory protection. There's no page level operations or permissions or so on. Things really are very primitive on a microcontroller. We're looking at CHERI, and if you've heard me talk any time in the last 5 years, I will have talked to you at length about CHERI. This is a really nice concept where you've got fat pointers that include validity, bounds metadata, and permissions directly inside the architectural kind of atomic capability data type. And this metadata for pointer access permissions and bounds is checked in the hardware at every memory access. So you can't kind of circumvent memory safety in a way that you can do in legacy C applications that just have raw pointers. There's prototype hardware available for CHERI, and we've got lots of that at Glasgow. Maybe some of you have too. If not, you can run things in an emulator or an FPGA as well. And the propaganda, that's not the right word, the publicity for CHERI says that it eliminates roughly 70% of critical vulnerabilities, things like use after freeze and buffer overflows and other annoying memory safety violations that cause critical vulnerabilities. CHERI, of course, is not ubiquitous. Microcontrollers definitely are. Tens of billions of microcontrollers are deployed every year. And at the moment, there are several thousand CHERI microcontrollers, memory-safe microcontrollers out there, like this one here. This is a Sonata board from Low Risk. This could be changing soon. There's a startup company called SCI Semi that's taping out CHERI silicon in a RISC-V IBEX core, and soon you'll be able to buy that. But for the time being, we want to get the benefits of CHERI memory safety in legacy language runtimes, because language runtimes like MicroPython really do have vulnerabilities that people are noticing and perhaps exploiting. So we want to try and make MicroPython more memory safe. A big idea then is differential fuzzing. So we're using a MicroPython runtime that's compiled for CHERI and running on a CHERI processor, and an equivalent MicroPython runtime on a non-CHERI system, and we run potentially problematic Python programs on both of them, see whether there's any difference in their runtime behavior, which might indicate memory safety problems. So a key research question is this: can CHERI serve as a practical oracle for interpreter memory safety? So we're going to generate some MicroPython programs that we think might be buggy or cause bugs on the underlying C runtime. We're going to run these programs on our two different runtimes in parallel, the non-CHERI traditional runtime and the CHERI memory safe runtime, compare the outcomes and try and find some problems and use that in some kind of virtuous circle to feedback. Okay, so I'm going to go through these 4 stages in a bit of detail here. There's the 4 stages up the top there. That's like our map here. And the first stage, we've got a few buggy programs. So this is a kind of seed for our corpus. And these come from bug reports, memory safety bug reports on GitHub, perhaps from the CVE database. There's a few MicroPython CVEs published in there. Also from other Python runtimes, we look at those as well and find buggy programs there too. We feed these seed buggy programs into an LLM. Yes, we're drinking the LLM Kool-Aid. We feed them into LLM and it generates lots more buggy or potentially buggy Python programs for us. And the way it does this is we give it a prompt that says, here is a Python program, generate me some more Python programs like this one. Get some more Python programs, and then we somehow assess these to see whether they're likely to be buggy, and then we use that to evolve the prompt. So this prompt here is evolving that prompt there, and we end up, after going around this loop a few times, with a set of programs that we then feed to a standard mutation fuzzing framework and generate even more programs. So these are what the LLM prompts look like. Here we go, look. Here is a MicroPython function, generate some test cases for it. And then that prompt gets optimized and evolved, and it ends up like this. So you can see this is a more detailed prompt here. And this is what we use to generate our MicroPython test cases. And then we mutate them using the standard kind of fuzzing operators that you'll see if you've done fuzzing for yourself, that somehow evolve, mutate the source code in ways that are going to do interesting things, hopefully. So the second stage then is this dual lane execution, where we run our potentially problematic Python programs on non-CHERI systems like this Raspberry Pi here and see what output we get, and also on CHERI memory safe systems and see what output we get. So MicroPython is running on top of one of these platforms, and we're going to see what the outputs are and capture things like standard out and standard error and maybe stack traces of errors and so on. Yeah, so in the non-CHERI lane, we run on x86 or ARM. We kind of sandbox our code and run it with a 10-second timeout and capture all kinds of dynamic information on what's happening. Do the same in CHERI, which is our memory safe runtime. And here, if we do have memory safety faults, we'll have metadata about those, whether out of bounds, whether it was an invalid pointer, whether there were alignment issues and so on. And we'll capture this data too in our CHERI lane. And then we compare the output from the non-CHERI classical execution and the CHERI memory safe execution and see whether we really have got a bug. So if you look at this Venn diagram here, right, these are the bugs from the non-CHERI runtime. Here's the bugs from the CHERI runtime. And where there's an intersection, then maybe that's that's definitely a bug that's triggered in both cases. Where we only see bugs in CHERI, that's a memory safety violation that's exposed by the enforcement of our memory safe runtime. And sometimes we get crashes in the non-CHERI world that we don't see in CHERI. And again, we'll look at these separately and see where they come from. There is a lot of duplication, to be honest, in our crashing programs. Often our mutants are just kind of superficially different. So we might run 2 test cases that expose the same bug. So we have to group these together or deduplicate our bugs. And we kind of look at the stack traces and the return codes and so on, and kind of cluster together crashes that are actually caused by the same underlying problem. And then we'll use delta debugging to minimize the crashing program to try and get a kind of minimum working example of the problem and feed this back into the LLM again to generate some more MicroPython programs and possibly use this program to report a bug to the MicroPython maintainers. Great, so that's the process. Very quickly, our evaluation. There's the non-CHERI platforms we ran on, and the CHERI platform was a Morello, which is actually a server class, 64-bit ARM processor, but we're running our embedded microcontroller C code on this platform here for now. We, in a 24-hour period, generated about 8,000 Python programs that were potentially buggy and ran them through these dual lanes. And yeah, the programs cover a range of different areas in the MicroPython runtime. Some things are looking at kind of raw memory buffers, foreign function interfaces, file system libraries, peripheral interactions, garbage collection, and so on. So you see here the 8,000 synthesized Python programs, which we hope are going to trigger bugs in our runtime. And indeed, we do find bugs. So these are the deduplicated problematic cases we found. So we ran, our experiments were really running on MicroPython version 1.20. So this is a few months ago when we ran this code. And we see there are more bugs on CHERI than there are on the non-CHERI system, which is because of the extra memory safety. We couldn't run an FFI on CHERI. We didn't have that working. And then we also looked at a more recent, this is practically the bleeding edge MicroPython here. And the number of bugs was reduced. The number of bugs was reduced. So they have fixed some of them, but there are still some bugs there. CHERI makes finding problems easier. You get precise localization of where the memory safety violation is. A bit like you would in something like address sanitizer or Valgrind, but this is much faster and also not random in any sense. These are kind of deterministic failures. And so we see, oops, sorry, my slides are going a bit mad here. We see, for instance, when we try to do array subscripting or memory subscripting, we get a CHERI fault straight away where there's a permissions violation, whereas that fault might not manifest until much later in a non-memory safe runtime where there'd be some kind of data corruption that would manifest itself in an arbitrary way later on. We reported some bugs to upstream MicroPython on GitHub. So here's one of the bug reports that Kai made. And this bug report was monitored and fixed in the open source project, the MicroPython on GitHub. Interestingly, we used an LLM to identify the bug, and Bob 10,042 used an LLM to fix the bug. But there we go. Yeah, so here's just a few examples of the kinds of programs that we synthesized which caused problems. So can I interpret this Python code in my head? Here's a byte array with some data in it. And then we take the address of the byte array. This is the MicroPython C types interface here. We take the address of this byte array, and then we get a memory view on the byte array. And then we realloc the byte array here. We're kind of growing it and making it bigger, so we reallocate the array. And then we do a garbage collection. And then we use this old view of the original array. We've still got a handle onto that. We're accessing memory that we possibly should no longer have access to. And this is, of course, a use after free, effectively, and a memory safety violation. Here's another one here. This is particularly arcane MicroPython code. And in here, we're redefining the comparator, and then redefining the comparator to clear our array reference, and then to do a garbage collection. And then we try to sort the array that we've just deleted. Oops, and we end up with an invalid array during the sort. So this is not very nice code at all, and in fact breaks the rules of Python, which says you shouldn't do things like this in comparators. Okay, so what we see there is that sometimes the code we generate is kind of causing a problem, but actually it's a problem because the API isn't well specified or well understood by the language runtime. Whereas this problem is a real problem and is effectively a bug that needs to be fixed in the MicroPython code. Okay, CHERI is very helpful for debugging. It helps us find our memory faults deterministically and quickly, and makes them much easier to classify because we have this metadata about what the problem is. And indeed, this gives us kind of better precision for using LLM synthesis for creating more test cases of a similar nature. Yeah, in terms of the validity of our experiments, we have noted some threats to validity. CHERI is a nice oracle, memory safety, but it doesn't detect all bugs. So if you have fields within an object, CHERI can't find intra-object memory corruptions. It's only working at the object level. Sometimes if your CHERI system doesn't do runtime tracking of capabilities, then you don't necessarily detect all use after freeze. And it's also the case that it doesn't detect other kinds of errors that aren't related to memory safety. So it's a good oracle, but it won't find all the bugs. Yeah, our seed corpus that we used in the first stage to generate these 8,000 Python programs is drawn from the CV database and other bug databases, but it might not be complete in its coverage of all Python patterns that cause problems. And we've only looked at MicroPython. There are other language runtimes that have been ported to CHERI, including from our friend Tomohiro C Ruby. So that might be another interesting runtime to play with, to look at that in the CHERI memory safe world and in the classical non-memory safe world. Also some WebAssembly runtimes too. So it might be worth looking at those to somehow strengthen the coverage, the broad coverage of this work. Yeah, so let me conclude by saying that this work carefully seeds large language models to generate a corpus of Python programs that is likely to expose memory safety bugs in an interpreter. CHERI is our efficient and effective memory safety oracle. So we use that to manifest the bugs and compare against a classical non-memory safe runtime. And we have identified real-world bugs, some of which we've reported responsibly and have been fixed in open source microcontroller runtime, particularly the MicroPython runtime. Thank you very much for bearing with us with our remote talk. And please do read our paper. And if you've got any questions, Kai and I are here and happy to take them now. Thanks very much, everybody.
So if anyone in the audience shouts out a question, and I'll repeat it to Jeremy because it has to be from here. Do you have questions? Well, let's start. Oh, Steve?
Yeah. In this really constrained environment, I wonder what role formal verification might have and whether that's part of what is considered.
Okay, so you have a question from Steve Blackburn, which is, this is a very constrained area, MicroPython, very small. Would formal verification be interesting in this space, and what sort of role does it play?
Yeah, definitely. So we've thought about things like model checking, or possibly looking at things like verification of certain properties interpreters in theorem prover like lean. Even though MicroPython is quite small, there are still some scalability issues with using these kinds of formal methods. So we're working on it, Steve, but we haven't got any decent results there yet. We'd be happy if you could give us some more pointers.
Thanks, Jeremy.
Cool. Any more questions? No. Nicholas?
Nicholas Van Kempen. So they use large language models to generate more bugs. So they'll run, large language models are trained to not generate bugs. Did they run into any issues in that process?
So you have a question from Nicholas Van Kempen? And it's, you're using large language models to generate bugs, but aren't large language models generally trained to not generate bugs? So did you have issues with that?
I think that's a really nice question, thanks. I'm going to invite Kai, who's also on the Discord here, to answer that question. Thanks, Kai.
Sorry, do you mean like using LLM to generate bugs and not generate non-bugs? Is there any difference like that?
Sorry, I didn't quite follow. Could you repeat?
Yeah, so I guess we didn't have trouble.
Okay. Cool. I think
Buggy code.
my experience is that LLMs do generate bugs. So I think we're out of time now because I think we're supposed to break for lunch. So thank you very much, Jeremy and Kai.
Thank you. Cheers.
Yeah, thank you.